Okay, so we'll continue with a definition. A series, sum an, is called conditionally convergent if the series itself converges, so if it is a convergent series, but the corresponding series of absolute values diverges. So this is the definition of conditionally convergent. So you are convergent, but not absolutely convergent. That is conditionally convergent. Example. So this example has a name, the alternating harmonic series. And we've seen this very recently. It was this series from the first example. This was the example B, minus 1 to the n plus 1 over n. So we've seen this does not converge absolutely, because if you look at the absolute values, you actually get the harmonic series, which we know diverges. So this does not converge absolutely. Now I claim that this does in fact converge. So if you do not take absolute values, if you just look at the series given, this series does converge. Now, for proof of this, I want you to look at the notes. So see notes for proof of convergence. Okay. So this is a series which converges but is not absolutely convergent. So this is conditionally convergent. NB, this is an important example. Remark. So why are we talking about all this stuff? Why are we talking about absolute convergence? Well, remember, we're trying to deal with power series. So for a power series, sum Cn, so power series centered at A, n equals 0 to infinity, with radius of convergence R. First point, the series converges absolutely. So not only converges, the series converges absolutely for absolute value x minus a less than r. Second point, the series diverges for absolute value x minus a greater than r. And undetermined for absolute value of x equal to r. So for different power series, you may or may not have convergence on the boundary when x minus a, the absolute value of that, equals r. So you must check these points individually. Okay? So this remark says that inside this open interval around a of radius r, you have absolute convergence. Because remember, for a power series, for different x, you get a different series. So what this remark says is that if x is less than r away from a, when you plug that x into your power series, you have absolute convergence. If you have an x that is further than r away from a, if you plug that in, you will diverge. And then if x is on the boundary, if it is exactly r away from a, you don't know. So you have to check these x's individually by plugging them into your power series. Okay, so we'll move on to our first theorem. If a series is absolutely convergent, then it is convergent. Okay, so what this theorem says is that absolute convergence is stronger than convergence. If you converge absolutely, you also converge. Okay, and this actually, if we think about it, there's some intuition behind this. What are we doing when we're looking at a series? We're taking these ANs and we're adding up more and more of them, and we're looking at the limit as we add up more and more ANs. Now, taking the absolute value of the ANs forces them all to be positive, the same sign. So when you're adding up all these little lengths, they're working together in their attempt to diverge. So if you still converge when they're all working together, so if you have absolute convergence, then you're going to get convergence when they're potentially working against each other, i.e. having positive and negative. Okay? So absolute convergence is stronger than convergence. Remark: the converse is not true. So convergence does not imply absolute convergence. Example, well, we've already seen an example. N equals 1 to infinity of minus 1 to the n plus 1 over n, the alternating harmonic series. This is a series which converges but does not converge absolutely. So i.e. convergence does not imply absolute convergence. And this is reassuring, otherwise our definition of conditionally convergent was pointless. So conditionally convergent was convergent but not absolutely convergent. Example. So we want to see how can we apply this theorem. So are the following series convergent? First example, sum n equals 1 to infinity minus 1 to the n plus 1 over 3 to the n. Second example, sum n equals 1 to infinity sine n over 4 to the n. Okay, so on the surface, these two series are quite complicated looking. You have an alternating series, and then you have this sine n in the second series that's going to have quite complicated behavior. So hint, test for absolute convergence. So see if you can make the absolute values of these ANs either less than something simple or equal to something simple. And if you can prove that these two series converge absolutely, then you're going to get that they converge. So at this point, pause the video, try and see if you can prove that these two series converge or not by testing for absolute convergence. Okay, so hopefully it's some time to attempt the questions. We're going to look at the solutions now. First problem. Sum n equals 1 to infinity of, now we're going to look at the absolute value like the hint suggests, minus 1 to the n plus 1 over 3 to the n. Again, if we take the absolute value of minus 1, we just get 1. So this is sum n equals 1 to infinity of 1 over 3 to the n. Now this is 1/3 over 1 minus 1/3. And this is the formula for a geometric series with first term a third and multiplier 1/3. And this is equal to 1/3 over 2/3. It's equal to 1/2. So our original series is absolutely convergent. So hence, sum n equals 1 to infinity minus 1 to the n plus 1 over 3 to the n is absolutely convergent. And hence, by the theorem, it must converge. Okay, because absolute convergence implies convergence. Second example, this one was a little more complicated. Sum n equals 1 to infinity, absolute value sine n over 4 to the n. Okay, so we have to work a bit harder with this one. Now, what is any series? Any series is a limit of partial sums. What's the definition of a partial sum? Sn is, well, you add up the first to n. So n equals 1 to n of sine n over 4 to the n. And we're going to look at the absolute values. So Sn is a sequence, and it's a monotone increasing sequence. What does that mean? So to go from Sn to Sn plus 1, I add on the absolute value of something. So I add on a positive number. So these Sns are getting larger, because at every stage I add on something positive. So it's a monotone increasing sequence. Hence, if I show that Sn is bounded above, it must converge by the monotone convergence theorem. So if you have a sequence that's getting larger and larger and it's bounded above, we have by the monotone convergence theorem, it must converge. And if this sequence of partial sums converges, that's exactly what it means for the series to converge, because the series is the limit of the partial sums. Okay, so I'm going to have to turn to a new page. Okay, so let's try to establish this bound. So sin n is stuck between -1 and 1 for all n greater than or equal to 1. We know this. So this implies that the absolute value of sin n is always less than or equal to 1 for all n greater than or equal to 1. Hence, sin n over 4 to the n, if I look at the absolute value of this is less than or equal to 1 over 4 to the n for all n greater than or equal to 1. Now, the term on the right-hand side is a much simpler looking term. So hence, Sn, we can bound this by if we were just to sum the 1 over 4 to the n's. And we only take the first n of them. That is less than or equal to if we're to take the limit, because all of the 1 over 4 to the n's are positive. But this is just a geometric series. So this is equal to 1 over 1 minus a quarter, which is equal to 4 over 3. Geometric series. Hence, Sn is bounded above by 4 over 3, and by the monotone convergence theorem, it must converge. So hence we've shown that the sequence of partial sums converge. That's exactly what it means for this series to converge. So i.e. equals 1 to infinity, Sn is absolutely convergent. So we showed that the sequence of partial sums where we're taking the absolute value converges. So this series is absolutely convergent. And by the theorem, this sum, sin n over 4 to the n, is convergent. Okay, so this theorem came in very handy because we had quite a complicated series. The sin n has strange behavior. It hops around as n gets larger. Yeah, it'll hop it from -1 to 1 and values in between that. So its behavior is quite strange. But we're able to, using the absolute value, compare that to the behavior of a much simpler series, a geometric series. So the theorem came in useful because it allowed us to compare this complicated series to a simpler one and show that it converges.